Okay, we're live. All right, so the first question has a very intuitive solution. Okay, so, but if you just look at the very next question, you'll see, well, it's not always simple to get like an intuitive solution to these. Because the first one asks, if the product of two positive numbers is 100, what are the two numbers that minimize the sum? Okay. By the way, if you weren't clear, optimization means to either minimize or maximize something. If you were doing this in like a business context, you'd be talking about maximizing profit or maybe minimizing costs or something like that. That's why they have like business calculus classes at most universities. That would be the main application, is looking for mins and maxes. So anyway, what does that have to do with calculus? Well, I'll give you a broad overview. If you have some function, how do you think you find this little local max here? Well, we kind of already talked about that, right? Mm-hmm. Figure out where's the derivative equal to 0. Mm-hmm. How do you find the max? Or sorry, the min. Same idea. So this is a lot of this stuff is focusing on the idea of, model some system and then say, when does that system have a 0 derivative? And that point you found should often correspond to either a local max or a local. Okay. The product of two positive numbers is 100. So what do you think I'm going to call the two numbers? It could be A and B. It could be X and Y. It's up to us. I think I'll go X and Y. So X.
W and B.
Could be. I do like A and B. Generally. X, but X and Y is fine. X times Y equals 100. Okay. So X times Y equals 100. So this would be, we'd call this a constraint. Meaning, it says, I want to make the sum of the numbers as small as possible. So you can't go, well, I'll just pick 1 and 1. Or I'll pick, right? You can't do that because that violates the constraint. So if you were to guess and check this, you might go, well, if X is 1, what does Y have to be? 100. So that's a pretty big sum. I can clearly pick 5 and 20. And that's a lower sum. 5 plus 20 is smaller. So, okay. By the way, Trey, you already got the answer intuitively, right? What's the answer to this question? 10 and 10, which you can think about it geometrically, right? I can phrase this question as saying the area of a rectangle is 100. What's the dimensions of that rectangle that would make it have the smallest perimeter, basically? Well, we kind of all know that that's like a classic result, right? It's a square is going to, right? I want to enclose a bunch of piggies. Is this going to use, is a 1 by 100 enclosure going to use more fence than a 10 by 10 enclosure? Yeah, this obviously uses much less fence. So, but I need to show you the technique because they're not always going to be that simple. So the constraint is X times Y equals 100, and we are trying to minimize, and this is usually going to be a thing you're trying to optimize. What quantity do we want to optimize? Well, in our case, the quantity, let's call it, the quantity is Q. Okay, the quantity we're trying to minimize is what?
X plus Y.
X plus Y. There's a really cool way to do this, which is like, if you do it the really hard way is to do it in 3 dimensions. I'll just comment on this briefly, but you could represent this as being, you could have an XY plane that's sort of like horizontal, and then have like a you'd have a third axis in the third dimension. And then this would actually describe a plane in space, a 2-dimensional plane embedded in 3-dimensional space. And then you draw this curve, X times Y equals 100 would live on kind of look like this. And then you would travel along this curve and figure out what's the lowest point on the plane that you hit as you travel along this curve. It's a pretty interesting way to do it. But anyway, that's beyond the scope of this class. I just thought I'd mention it because it's kind of neat. If you take calculus 3, you'll do a lot of 3-dimensional stuff. So, that's typically the first class you take where you start really going into 3 dimensions and stuff. So, okay. So here's the idea. I'll cut to the chase here. I don't want to have two variables, right? In math, we always, if we can do our whole problem with just like one variable, it's much easier. So what's the substitution I want to do? I'm going to replace this y with what? 100 divided by x. You guys feel okay about that?
Yeah.
Sorry, this marker's a bit faint. Put that in the box.
It needs to lie down for a while.
I thought, what if I kept all the markers? And then, I don't know, could some artistic person use them to make an art project or something?
Yeah, I mean,
You
we're
think so?
doing trash art right now.
Doing
so-
trash art?
Yeah. Yeah, but I know what I'm saying, we could probably do something with X marker.
Okay, maybe I'll hold on to it then.
Yeah. But nobody thought that my
Just have the
pen
back,
was funny.
just unscrew it.
The marker,
Eat your X
It's fine.
So,
oh, it needs to lie down.
I don't know. You'd have to talk to the expo company. Anyway, now think about this equation that we have. So the quantity that we're trying to minimize, you can describe it in terms of one variable. It's the x value you pick plus 100 divided by that x value. So now you can represent this, right? How does the quantity that we're trying to minimize depend on our choice of x? So visualizing it would look like that. We hopefully kind of have some sense of what this would look like, right? There'd be an asymptote at 0, and then what's the end behavior like? What happens as x gets really big?
The page is one. Or, I mean, infinity.
Yeah, so if x was 1,000,000, can x be 1,000,000?
Okay.
X could be 1,000,000, and y would be 100 millions. That'd be a really skinny fence for the piggies. But the idea is this graph, this is one of the many reasons why I try to get you guys to understand graphs, is because when you're doing mathematics, like especially calculus, doing a question like this, if you can understand that this equation looks like this, if you have like an intuition for that, then there's a nice local minimum right around here. And you know that your process is going to generate a nice local min, or it's actually an absolute min in this case. Okay. Now, by the way, if I graph the entire thing, I'd also have a piece over here, right? But there's a thing. Can x be negative? Yeah. The part of the constraint, really, if I want to get technical, the constraint also says that x and y are both positive numbers. Okay. So if you're being very thorough and complete, you'd include that as part of your constraint, okay? Okay, now how do I find that point? Well, the procedure is pretty straightforward. I'm gonna take the derivative of q with respect to x, so x is my variable. All right, what's the derivative of that? 1 minus 100 over x squared. Is that we're okay with that? Cool with that? Okay, so that describes the derivative. You can see already, if you plug in a really small x value, like if you make x 0.00001, you'd have an enormous negative slope, which we can see in the graph. If you plug in a sufficiently large x value, what's the slope of the curve? That's maybe a more interesting question. If I plug in a gajillion for x, what's the slope of my curve? It'll be very close to 1. Very good. Very good. Everyone understand that?
Yeah.
If x is enormous, this term would be 0. Okay. So what do? We set it equal to, set it equal to 0. And so this is a fairly easy equation to solve, right? 1 equals 100 over x squared. X squared equals 100. So x is going to be 10. I reject the negative solution because it doesn't obey the constraint. And of course, getting the y value, once I found the x value, the y value follows very easily. So it turns out that this is 10. What's this?
Also 10.
0.
I was looking at the
Don't do that to me. Oh, the slope is 0. That's true. 20. The quantity is 20, right? Because what's the quantity? The quantity is x plus y. If x is 10, y is 10, the quantity is 20. So,
that makes sense.
that makes sense? What?
Come
So
full
we've
circle.
gone full
Are they
circle, so now I
asking-
understand.
So they're asking for,
You understand? Yes, I did.
Negative go in front of the 100 for each bit.
So I just added this term to the other side.
Oh, you got that.
Okay, so you can think of this as a proof. Back in geometry, most likely you just said, you maybe just sort of conjectured that the square is the minimum. A square minimizes the perimeter. And then maybe you just looked at like, well, if we do, if I pick two numbers that are, you can kind of show a very intuitive argument that's pretty strong, but doesn't prove it for
I just
sure.
looked at its factors. And I like the smallest value.
Okay. Keep in mind though, the answer to a question like this could certainly be irrational. Like, does that make sense?
Yeah.
So if I said, what two numbers, a very simple example is, what two numbers that have a product of 5 have the minimum sum? Well, it's root 5 and root 5. So you got to make sure, I think it's really smart to look at factorization for a question like this. Certainly a great
wait,
first step to take. Yeah.
so is the final answer is asking for the constraint, right? Not.
It says, find the two numbers. So the two numbers would be 10 and 10.
Okay, that's what I thought.
Yeah, so
You just threw me with the 20. Like, I get where you got it, but I didn't know if that was supposed to be part of the answer or not.
not technically, yeah. Because the question might be phrased, what is the minimum sum? Right? So there's a difference. The question of what are the two numbers that produce the minimum sum? That's 10 and 10. If the question said, what is the minimum sum? You'd say 20. Okay.
Cool.
Okay, so as you can see, there are several substitutions happening all at the same time here. Or maybe not at the same time, but the same problem. There's some, you gotta be very comfortable with substitutions. You gotta be able to go, oh, that equals that, so I can sub it. Let's do, why don't you guys try to set up number 2? So very similar question, but you're trying to, this time read carefully, you wanna minimize the sum that's twice the first number plus the second number. So you're no longer minimizing x plus y. Okay, so hopefully you got that written down as your first step. The
Yes.
constraint is x times y equals 288. That number hopefully looks a little suspicious to you. Well, it's double a very famous number.
Famous, wow.
Famous.
Wow.
Dixie
Yes.
D'Amelio of numbers. Well, it's at the
Yes,
very,
yes, yes.
it's the last number on the standard times table. Man, only true third grade geniuses can know what 12 times 12 is.
No, I wasn't a third grade genius,
You were,
not
yeah.
gonna lie.
99.9% of Alfred Eisensteins don't know what 12 times 12 is. If you were the true third grade genius, you knew what 13 times 13 was. It wasn't even on times table.
Yeah, of course.
You could really flex on them.
Yeah.
I didn't attempt to get into higher math until I was in middle school. Oh, you can't expect me to be a
Wow.
third grade genius.
And then 14 is easy to remember because it's just a flip, 196.
Third graders destroyed by facts and logic.
Facts and logic.
Okay,
225.
so
I just got
But I
tired of
don't
not
really
being in
get
math
it.
with all
same idea here. So,
I was terrible at times tables.
I loved
When
time
they
too.
made me do the math under pressure, I was like, hell no.
All those
That was the
time
one thing
things.
I got novice. Yeah, I got novice on every single
I did
time
too.
table ever.
I once finished 3 of those pages in a minute.
Yeah, that's wild.
sorry I had a nerve.
It wasn't a nerve. It was
Like,
It was a
well,
moment
I
of
loved
glory
math,
for me.
but
Are you
times
kidding me? I
tables,
loved those
like,
things.
I hated times tables.
I didn't do nearly as well on.
Okay, so
Math makes me calm, and that is not coming.
this is the substitution.
My plan is to make everyone cry.
It made everybody cry.
Like if you cry every time.
Like if you
I feel like that's just math
So,
teachers.
as you can see, it's the exact same question, so it's just a little bit different this time. And I put this on here to point out that you're not always going to have a perfect symmetry in your answer. So in this case, because of this, it's going to weight the answer a little bit. Meaning we kind of want x to tend to be smaller than y, I think, because we're doubling x in our quantity and we're trying to minimize that quantity. So it's almost like the x's cost more than the y's, in a sense.
Yeah.
Anyway,
Boom.
take the derivative.
Brain destroyed.
2 minus 288 over x squared. We're going to set that equal to 0. Again, we want to know, when does that tangent line be flat? When do we hit that minimum? If I solve this, what do we get for x when we solve this? 12. Okay. Now the answer you get is actually very, I think it's very intuitive. What is the y value going to be then if x is 12? 24.
Ah! Oh, goodness.
Oh.
And you can do that mentally by going, you're not like, if someone can look at that and go, oh, if x is 12, y is 24, they're certainly not doing this in their head. That's probably not the case. They're just probably going, well, 12 times 12 would make half of that number. So
Yeah.
12 times double 12 would make double 144.
Yes.
And Thinky Winky, yeah, that's the best Teletubby. Everyone knows that. Okay, so now it sort of makes sense, though, hopefully, that it stands to reason that because x is twice as expensive as y, you see what I'm talking about with expense thing? It's to be like, oh, xylophones and what? Vibes?
Yeah.
Sure. I was trying to think of a word that started with a Y, but I couldn't come up with one. Yaks. Xylophones and yaks. Well, xylophones cost twice as much as yaks.
Why?
So the combination that's going to minimize the total cost of xylophones and yaks has half as many xylophones.
Are these like diamond encrusted xylophones?
So we're done, right? Guys, a quick little clarification. 3 and 4.
Most people.
The answers are, I would say, kind of obvious what they're going to be. You have to show that those are the answers using calculus, just to clarify.
Yes.
Spoiler alert, the answer to 3 is 9. Or it's 9 by 9, so it's a 36 perimeter, but you have to prove
Put a
that.
little
Prove it
nine.
using calculus. Thank you, Aspen Toad.